Hello, I'm Mike Leese. I'm the founder of µCurrent. Today I'll be giving you a demo on our µCurrent probe. After the demo, I'll give you a tip that could help out with your current measurements. Let's start out taking a look at some of the features of the probe. On the right side in the center we have our scope connection. We'll work with any scope with a standard BNC probe connector. To the left is the zoom view selection switch. We have a normal view, 10x zoom out, or a 10x zoom in. Normal view is either 1 nanoamp per millivolt or 1 microamp per millivolt on the output. And on this edge we have the DC power connector. On the left side of the probe we have our range selection switch. Gives you 3 options. Precision mode measures as low as 2 nanoamps, and wide range mode will go as high as 400 milliamps. And external resistor mode, you can use a sense resistor on your target board, optimized for the current range of your product. We also have the target system connector here. We accept input voltages from 0 up to 20 volts DC. It'll cover all the common small battery voltages from single, AA, AAA cells up to solar panel charged 12 volt lead acid batteries. This range also covers the output of most common small energy harvesting power sources. So that covers features. I'll get the demo set up and be right back. Okay, so here's our demo setup. It's easy to set up. We just plug in our power connector, hook up our scope. Our target system today is this circuit board from a small Bluetooth powered or enabled battery powered product. It has some interesting aspects that we'll take a look at here in a minute. And as you can see, we have the probe hooked up in line with the battery voltage. We have a waveform on the scope, so let's get zoomed in on that and see what we have to see. So for setup today, we have the probe set on the wide range mode. So we'll go down to 1 microamp measurements up to as much as 400 milliamps. As you can see, we have our scope set for 2 volts per division. So essentially we're looking at 2 milliamps per division here, 250 microseconds per division on time scale. So, and see this device wakes up approximately once every second, does a little housekeeping and goes back to sleep. We take a look at our cursors here. We can see that typically we're peaking at roughly in the 9 milliamp range, 8.8 here. Drop the cursor down at this plateau. So after we wake up, we do our housekeeping. We're running not quite 4 milliamps, 3.76 milliamps, and this whole event 5/6 division, so a millisecond and a quarter to 1.5 milliseconds. We can also zoom in a little bit here, see what there seems to be some activity here before this event actually occurs. So we'll zoom in. We'll come down here at 50 millivolts per division. Essentially, stop this so we get a little cleaner view. So these are little cyclic events. Approximately 800 microseconds, the micro wakes up, does its tick interrupt function and goes back to sleep. And as we see right here, we're looking at about, so let's call it 40 microamps. And we see that this particular event takes somewhere 50-75 microseconds. Now if we wanted to, we could change over to the precision mode, really zoom in there and see what we're doing. But yeah, this looks pretty straightforward, so we'll just leave it at that for now. Change our setup here again. We're going to go 5 milliamps per division. And in this particular device, we shake it to wake it up. My apologies. apologies there, I had the wrong time scale. So, are we awake? Okay, we have our device woken up now. This waveform on the screen's a Bluetooth advertising sequence. So check our setup here again. We're at 5 volts per division, 5 milliamps per division, and we're on a 500 microsecond per division time scale. So let's stop this and take a look at what we have. So, again, using our cursor, take a look at this first peak. Similar to what we saw in the once per second event, a little under 9 milliamps, what we're seeing here. We can go up and check these 3 peaks when our transmitter is transmitting, and we're right about 17 milliamps at those peaks. These intermediate peaks, again, about 9.8, not quite 10 milliamps per division there. And then our plateau after our radio activity, code does some more cleanup and goes back to sleep. We're looking at about 4 milliamps per division here. This waveform is somewhat distorted. It partly has to do with where we're looking in the system, since we're right on the output of the battery. That really concludes the demo. Hopefully it was useful and gives you a good idea of what can be done with our µCurrent probe. So thank you for your time. As you saw in the demo, our µCurrent probe allows you to view waveforms at a variety of current levels without having to play around with different resistor values. We're able to examine current levels from 40 microamps up to 17 milliamps by just changing scope settings, and we're nowhere near the limits of the probe or the scope. The combination of the high-gain amplifiers in the probe and its zoom view capabilities allows you to get away from using your scope's lowest volts per division setting. This is important because that's typically a scope's least accurate range, and the error can be a significant percentage of the signal or even larger than the signal you're trying to measure. Before we conclude, I mentioned earlier, give you a tip to make your current measurements easier. The high-level block diagram here shows a simple device similar to what we used in the demo. Starting from the left side, there's a battery power source, a voltage regulator, and output capacitors. And on the right, there's a wireless radio module, which could be any relatively high current device like a GPS receiver or a small motor in a robotics application, and then the remainder of the circuitry. I mentioned the interesting waveform distortions during the demo. These distortions were primarily a result of where we were looking at the current flow, essentially at resistor A in the diagram. Unless you're simply looking at current draw for battery life calculations, this really isn't where you want to take your current measurements, and there are several reasons for that. First, the battery and voltage will vary from its state of charge, output load, temperature, age, and other factors. With a device doing the exact same thing, the current measurements you take with one battery can vary considerably compared to another battery, or even with the same battery at different levels of discharge. For the device used in the demo, the battery voltage will drop from 4.2 volts when fully charged to just above 3 volts at the cutoff. And the peaks in the last waveform we looked at will range from 17 to 26 milliamps depending on the voltage level. The second problem is the output of the battery. You're looking at a waveform of the combined current draw of everything downstream from the battery. Now, that can be a huge problem when you're trying to determine if your power management firmware is working and the micro is going into and out of sleep modes as expected when other activity is going on in the system. And thirdly, if your circuit has a switching voltage regulator, then both at locations A and B in the diagram, you can see large current pulses as the regulator is charging its inductor and output capacitors. We move to the right at location C. You certainly get a much cleaner waveform here, but the waveform still shows the combined current draw. If you're using a device like a wireless radio module that has its own integrated micro, it would be nearly impossible to determine if the events you're seeing on the waveform are due to the firmware in your micro or the firmware in that device. The resistor location D is ideal for analyzing current waveforms, since they're separate sense resistors for your micro, the wireless radio, and the remainder of the circuit. Not only can you examine the waveform created by the firmware on your micro, you can also look at that waveform down in the nanoamp range to see if it's the micro is sleeping or operating while the radio is transmitting and maybe drawing several hundred milliamps or even a couple of amps in a cellular application. So, that concludes our video. Thank you for taking the time to view our demo today. You can find the spec sheet for the µCurrent probe along with white papers on low current measurements on our website and additional information on low power design on our blog.